Hi Kidlets, this is your first notes video for stellar evolution, the life and death of stars, and the difference between sun-like and massive stars. The first thing we are looking at is the ways in which we measure stars. I had the cutest picture in here of a star with a smiley face, and it somehow didn't make the transfer to this app. So as we've already looked at, we see this correlation between color and temperature. And we indicate that in terms of stars with spectral class. So the spectral classes that we have discussed are O, B, A, F, G, K, M, and we're not going to look at L and T, which are dwarf stars. But these are determined from the atomic spectra, which is also indicative of temperature. And we can see just by looking at the variety of stars here in each of these different spectral classes, we can see various different sizes, colors, and all of those things can give us lots of information about the star in terms of its life cycle and its composition. So we know that all stars have relatively similar compositions when they begin their life as a star, but their temperatures are vastly different, and that temperature then determines the rate at which the chemical reactions happen. When you have thermonuclear fusion within a star, and then the rate at which the composition on the interior of the star begins to change. So they're all initially predominantly hydrogen, but that changes throughout the star's life. So we've already taken a look at this, but seeing the correlation between a star's color, what spectral class it would have, and seeing that yellow, this would be for our sun, and then the correlating temperature for each of those stars. So we can see an exponential difference between our cool red stars and our hot blue type O stars. And as we'll see, there are far greater implications besides just a high temperature in terms of the fate of that star caused by that temperature. So we know that every star has various different temperatures, luminosities, and sizes, and we ordered these within a Hertzsprung-Russell diagram, or an HR diagram, which is basically a way to plot each star on a graph by measuring the star's brightness against its temperature, which again, temperature and color we can think of as synonymous. However, what the HR diagram does not include is locations of stars. This is just giving us information about a star or a star cluster itself. So the diagram was created around the turn of the century in 1910 by two scientists at Harvard University. And I've talked about the women at Harvard significantly in class, but this gave us this major step towards understanding stellar evolution, or the way in which stars undergo sequences of dynamic and radical changes over time. And these two scientists, A.N.R. Hertzsprung and Henry Norris Russell, were using data compiled by Miss Maury at the Draper Observatory at Harvard, in which she was one of many women who were very bright, and using spectral classification that they took, that they formulated from observations at the Harvard University. So here is a sample HR diagram, and I've left this guy blank. We can see that we have temperature along our x-axis. Our luminosity is along our y-axis, and we can see the L here and then /L sun. So this is based on the luminosity of the sun. Our sun is always our starting point. But we can see that we also have other axes here. We have spectral class across the top, and we have absolute magnitude on the side. Now, briefly, there is a difference between absolute and apparent magnitude. Absolute magnitude has to do with the intrinsic brightness of the star, which is not distance dependent, whereas apparent magnitude is how we would view it from Earth. For example, the brightest star in our sky is obviously the sun. However, as we'll see, the sun on the HR diagram is actually only about here. It is not a very large or bright or luminous or big or hot star. It's only somewhere around here. So we could see that it's got a pretty low temperature, and actually according to the way this HR diagram is laid out, our sun would actually be over here. Most HR diagrams place the sun towards the center because that's kind of the way we think about it. But our sun only has a temperature of about 5,600 Kelvin, and we can see that this HR diagram goes over to 34. So we have increasing luminosity towards the top, and we have increasing temperature towards the left. And as we will see, we can plot most stars on this HR diagram. What we end up having is a region where most stars fall. We call this our main sequence. We end up having a region right here of white dwarfs. We end up having a region up here of hypergiants and supergiants. And then we have another region right here of red giants. And this is generally the way that any HR diagram would look, is broken up into these regions based on luminosity and temperature. So the HR diagram can tell us which type of star we have, and we would plot them according to their associated temperatures and luminosities. So the main sequence is where most stars fall, but within the main sequence we actually have some different types of main sequence stars. So we can have low mass, medium mass, and high mass main sequence stars. So this we could think about as the middle of a star's life. Just like people have a middle age, this is the middle age of a star. And if you think about the middle age of your life as being from approximately, 18, 20 years old when you enter adulthood to the time before you are elderly, that's about 90% of your life. So we can have dwarf stars, main mass main sequence stars, and high mass main sequence stars. Think about this as the height at which you are when you enter adulthood. For me, at 5'1", I'm never going to be a tall person. I will not continue growing. So in the same manner, we don't have dwarf stars that then become medium mass, that then become high mass. The mass they are born with is the mass that they keep, and that's an important distinction. And that's one area of discrepancy that I run into every year with students, is they seem to think that this is the life cycle, and it's not. This determines the life cycle, but if it is born a dwarf star, it stays a dwarf star. However, these patterns right here, a giant star and a supergiant, that is a phase of evolution, as is a white dwarf and as is a black dwarf. But as we'll see here in a few moments, we have not found any black dwarfs. These are a theoretical item. We know there must be some out there, but we have no means of detecting them. So our sun is a type G star, a type G2 star actually, on the main sequence. So again, from our previous slide, we would find that under stellar classification G associated with the luminosity of our sun, which would be 1 because it's the baseline, and the correlated temperature of about 5,600. I apologize, this slide came out funky. These backgrounds in my PowerPoint are white, and for some reason they transferred black here, and I'm not sure why that is, and I apologize. So the HR diagram gives us a lot of information. Again, the location it can't give us, but we can interpret somewhat of a distance. But more importantly, we can look at radius, mass, the luminosity, and then also the age of a cluster. We can think about, as we're learning this concept, about plotting individual stars. But what's more important is to plot the age of a cluster, because stars in a cluster are going to have approximately the same age. Just like all the stars in our night sky are approximately the same age as the sun, because they were born from the same molecular cloud. Remember that we've talked about how molecular clouds had to undergo some process of disturbance that caused that molecular cloud to rotate, to heat, and eventually collapse and form accreted products that then became suns or stars and then planets. So stars that are in the same region are going to have approximately the same age and similar characteristics as well. So by plotting them on an HR diagram, we can determine these things. So here is a sample HR diagram. We can see our main sequence. We can see how the color changes according to spectral class as we go from right to left. It is actually kind of opposite going right to left. You can look at it left to right, but we go smaller, bigger this direction. So we can see some blue giants, we can see red supergiants, and we can see red giants. Here would be approximately our sun. You can see that the axis of this HR diagram is slightly different than the one we saw previously. So putting the limit out here at 40 places the sun a little more towards the center. We can see our luminosity classes on the side, and we can see how the size tends to change as we go up the main sequence. So remember that we have those different types of main sequence stars. We can think about our dwarf region here, our mid-size main sequence here, and our high mass main sequence up here. And remember, they do not go from one to the next. They don't do that. If they start out a dwarf star, that is where they stay until they reach a later stage in their evolutionary process, in which case they would then migrate off of the main sequence. So radius and overall star size are something that we can plot and also interpret from the HR diagram. And notice that here we have many stars, not just a single star. So this serves us better to plot regions of sky or star clusters instead of just a single star. So we can see these dashed lines here, and they're not vertical. These are at an angle. So anywhere, somewhere along these lines, these are lines of radius. And if you look really closely here, you can see that this says R sub S. So this would be the radius of the sun. Remember that the sun is used as our baseline. So if it's R sub or 1 solar radius, here's 0 solar radii, here's 10 solar radii. And notice that this is just along the main sequence here. So as we move out here, notice that we have a new radius line. So 100 solar radii and 1,000 solar radii. So these are not vertical, these are diagonal. So, and then we can see those correlated here. Stellar radii is an important determination of how long a star is going to live, because higher mass stars, even though it may seem like they have more fuel, they actually burn through their fuel much faster than stars that have a lower mass. So we can see this directly correlates to stellar lifetimes. If we have a star that is only about 10% the mass of a sun, it can live up to 3 trillion years. So these stars are going to end up outliving essentially the estimated lifetime of the universe. Our sun will live about 10 billion years. It's about halfway through that life cycle. And by the time we get up to these stars that are higher on the main sequence, their lives can be as short as 30 million years. So that's a significant difference between stars of much lower masses. And the reason is that stars of high mass burn through their fuel faster. You can think about this as analogous to a gambler. Someone going to Las Vegas. Hopefully you've never done that because you're too young. But if you go to Vegas and you show up with, say, $10 versus someone who shows up with $1 million, think about who's likely to make higher bets. That's basically what stars do. The ones that have more fuel burn more fuel. The ones that have less burn less, and they burn it slower. So here we can see a basic chart showing the expected lifetime versus solar mass. And then we can also see a correlation to spectral type, because remember, the higher up on the main sequence it is, the hotter it's going to be, and that then alters the spectral type and in turn the color. So the smaller stars are going to live significantly longer lives than high mass stars. And the consequence of this is that we don't see a lot of high mass stars. We have a universe that is very much dominated by lower mass, cooler stars. So we don't see a lot of these type O, type B stars. However, the early universe did. The very first stars, long before there were galaxies or star clusters, the very first stars were very hot, very big, very luminous type O and B stars that, as we'll see as we get into the fate of high mass stars, these then resulted in supernovas, which dispersed elements, which caused other molecular clouds to condense, triggering more star birth. And then after you had about 8 billion years or so, we started to see the formation of galaxies, of gravitationally bound star systems. But the very first stars, long before galaxies, were these very hot stars, and we had to have those to be able to populate the universe with heavier elements, which could then be incorporated into new stars. So here we can see a globular cluster, which is different than a galaxy because these are just smaller. These can only be about 30 to 50,000 stars, where you can see galaxies that can be hundreds of thousands or millions of stars. So this would be, you can think of it just as like a mini galaxy. And we can identify how old a globular cluster or a region of sky is by looking at the turnoff point. A turnoff point for a star on the diagram is when we see that the majority of stars begin to leave the main sequence. So as we start looking at the fate of stars, of sun-like stars and of massive stars, we'll see that when they burn through all their fuel and they move off the main sequence, as their luminosity changes, their location on the HR diagram does as well. So remember, stars do not do this. They do not move up the main sequence, but they do move off of it. So by plotting where this turnoff point is, we can get a really good estimation of a cluster's age. One thing that's important to note, and one of the reasons that we see so many low mass stars in the universe, is that these very low mass, cooler type M stars that are about 8% of the sun up to, say, 10% of the sun are also, they're so small and cool that they have enough hydrogen to sustain hydrogen fusion using the proton-to-proton chain, but they don't have enough mass to create temperatures and pressures to fuse things that are heavier. So these never go on, stars down here will never then go on to fuse carbon, nitrogen, and oxygen like sun-like stars will. So these stars essentially have no turn-off point. So all of their hydrogen is available for fusion, but their temperatures are so low that those main sequence stars' turn-off point would be measured in trillions of years. Our universe isn't old enough to actually have that. So, for example, the lifespan of a 10 solar mass star is 6 trillion years, which exceeds the current age of the universe. So all red dwarfs are essentially main sequence stars. So even though they're very long-lived, they will eventually run out of fuel. And once it's all been fused and that nucleosynthesis stops, that remaining energy, that remaining helium will cool by radiation, it'll contract, but it will never become a red giant, so it won't have a turn-off point. Stars down here would then just move over to the white dwarf branch, but we wouldn't call that a turn-off point. The turn-off point is when stars turn to become giants or supergiants. One thing that I would expect you to recognize if shown a few different HR diagrams is that you could recognize from the turnoff point what the approximate age would be. And if you notice, this one does not have all of the stars that have even reached the main sequence. So we can see that for this one, it must be very young. There's no turnoff point whatsoever. So the point at which all of these guys, all of these stars reach the main sequence, that's when they begin actually having fusion. Out here, these are only visible in infrared. We wouldn't really call these stars at all. They would only be visible within an infrared dust cocoon. So we wouldn't be able to see them in the visible. So this would be a very young cluster. Notice there's nothing over here in the giant branch. So stars become giants, and then for sun-like stars, they will eventually cool to become white dwarfs. So if we remember, this is our giant branch, and this is our white dwarf branch. And this has neither. So that indicates that this is an extremely young cluster. And then we get over here and we start to have a turnoff point. So here, this would be our turnoff point. It's high on the main sequence, which means it's older than this cluster, but it's still not super old. We have 2 white dwarfs. We start to see some of these in the giant branch. But then if we look at this guy, we can see that this turnoff point is even lower. And now we have a really well-formed region within the giant branch out here, and we have more white dwarf stars. So this guy would be the oldest, as indicated by the turnoff point, the region, the giant region, and then the white dwarf region. The white dwarf region specifically indicates the old stars. So as you see, high turnoff point here, less white dwarfs. Low turnoff point here, more white dwarfs. And then as we get into D, notice that this has a lower point of the stars reaching the main sequence than this does, and we do have a turnoff point. So that means if you were to actually place these in order, these guys in order, this guy would be the youngest, followed by this guy, followed by this guy, followed by this guy. If you don't understand that, you may want to watch this part again. I would definitely expect you to be able to recognize and apply that. And again, looking at where they meet the main sequence, where they turn off the main sequence, the giant region, and the white dwarf region. Those are your clues. So if we were to look at the region around Earth, up to about 62 parsecs, and remember a parsec is 3.26 light years, we could see all of these stars plotted, and they are generally the same characteristics as our sun. And if we were to put that in a graph, this is a cool little 3-dimensional bar graph, we can see that the majority of stars in our stellar neighborhood are red dwarf stars. We can see that then we have a significant number of white dwarfs, which tells us that our cluster is kind of old. It's old enough to produce white dwarfs, which takes about 5 billion years. But then we can see a very small number of giant stars, and also a small number of very low luminosity main sequence stars. The other reason that we have a hard time creating a survey like this is these really faint stars are really difficult to observe. So we know we have very few of the massive stars, very few supergiants, but really faint stars, the ones that haven't quite reached the main sequence yet, those are challenging observationally. So next we're going to be looking at binary stars. Over 50% of the stars in the galaxy are binaries. We also see them in groups of 3 and 4. Our sun is actually unique in that it does not have a companion star. So these are pairs or multiple systems, and they orbit a center of mass. And that's important. They don't just orbit each other. We can see that here we have a center of mass in the system, and this is determined by the mass of the 2 companion stars. And we can see here that this center of mass is closer to star B, which is an indication that star B is more massive than star A. So the more unequal the masses, the more it shifts towards the more massive star. And as we've already talked about with orbits, we could use Kepler's laws to then determine what these masses are based on their orbital period. Binary stars are really important for mass determinations. Again, by using Kepler's laws and being able to calculate the period of the binary stars, we can determine then what their respective masses are. The ideal situation, of course, is a visible binary, and I'll show you guys a video of this in class, and that would be where we can physically see their orbital periods. But of course, as you can imagine, these have to be very close in order for us to do that, and that's usually not the case, being that our closest star is 4.2 light years away, and it is not a binary. What we see usually is a spectroscopic binary, and again I'll show you another video of this, but this is where we can use the Doppler shift and then interpret that to be able to infer an orbital period. So the Doppler effect as it applies to binaries again is if it is blue shifted, we would see it coming towards us, and if it is red shifted, we would see it receding from us. And we can see with these spectral lines, so if it's approaching, we see these lines shifted to blue, and if we look at those same lines as it's receding, we see these shifted over. So this line was this line, and this line was this line. And we see this red line here that is shifted more red. So we just see everything shifted, whether it's approaching or receding. Another type of binary that we have is called an eclipsing binary, and these can be determined, and this is actually what the Kepler spacecraft uses in order to search for extrasolar planets. It determines a change in luminosity of the star by looking at a light curve of the star, and we can use this for stars and for planets. So if we look at this right here, we can see a light curve. That's what this is called. And every time you have a dip is when you have a decrease in brightness. So when you have the smaller star go in front of the bigger star, you have this dip in luminosity. Then you have even luminosity as they're next to each other. But if you notice right here, we have a secondary eclipse. The reason that we have that is because if you take a look at this star, its companion is behind it. Here, you have the luminosity of 2 stars. Here, you have the luminosity of 2 stars. Here is 1. So it's a secondary eclipse because it goes behind, overall decreasing the luminosity of the entire system. And then when that star passes in front again, we have a second primary eclipse. Again, I have a video to show you in class, but eclipsing binaries are important because when we look at those light curves, we can then determine the orbital period based on the periodicity of the eclipse. That is all for your notes. I'll see you in class.